else to get started. So, and I will get to that after. Thank you so much.
So thank you, Vivian. And so I continue where I left off. So remember we introduced discuss mixing in general and some mix norms. So norm way to quantify. Sorry, I decided. And measure ways to quantify mixing, and now we want to study rates and see whether those rates are optimal. So let me start. So remember there were three cases. One where we had like a constraint on the subalert norm below the norms in terms of the gradient, so for example, constraint on the energy, and then situation where we control the gradient in NP, and then iron. And so the first example is when we control things like the energy, so norms that are, norms that don't involve the gradient or control the gradient by in a very weak sense. And in this situation, we cannot actually have finite time mixing, but so perfect mixing in finite time. But let me make one comment first. The transfer equation is time reversible, and theta equals 0 is always a solution. So finite time mixing can only be possible if you have non-uniqueness of the solution. Because you can reverse times and you will have the zero solution and the time reverse solutions that are perfectly mixed. And so, but dependently on Ambrosian theory, you know that this will be impossible if you have an S-sphere from this strength. So let's look at if you have an energy budget. So that means you control uniformly in time the L2 norm of the advective velocity. And let's try to see if we can get a lower bound on the mixing scale. And in this case, you can simply do by energy estimates, which will not be the case if you control higher norms. So you do a simple energy estimates, and one nice way to do that is to introduce a potential. So you write the scalar, so theta is the advective scalar. You write it as the Laplacian of some H2 potential, and then the H minus 1 norm is exactly the H1 norm of phi, or the L2 norm of the gradient phi. So if you integrate by parts, what you have is that the time derivative of the sorry, this is a misprint. It should be the minus 1 norm square. Okay. So you have a time derivative of the minus 1 norm is bounded below by the product of the energy times the L2 norm. In other words, if you integrate now this, you get a linear lower bound. Okay. So what we expect by doing energy estimates is that we're going to have a line, a linear lower bound that will meet 0 in finite time. If you do it under an entropy constraint, you will get also a linear bound, while the optimal bound will be exponential. And if you put a higher constraint, you're going to get a Gaussian bound. Okay, so that's what you get by energy estimates. And none of this will be optimal except in this case. So the linear lower bound will turn out to be actually optimal. So in other words, I will construct this very simple example of a flow that achieves finite time mixing. But this example is only for one initial conditions. But nevertheless, it's very instructive, and I will try to explain why. So here is my example. So I should say that we rediscovered it, Charlie and myself and other collaborators, but in fact it was already implicitly present in the work of Valberto Balsan, and in a slightly different configuration also in the work of Nicolas Depot. And they were actually interested in non-uniqueness of the solution, and I will come back to the issue of non-uniqueness a little bit later on. So here's a very simple example. So we take a binary function again. For many of these examples, we will evolve the only binary functions. for the reason that I explained in the lecture this morning. So the sets where you are 1 or -1 is exactly half. So in other words, my initial condition is a strip. So the square denotes the periodic torus, and I take half of it to be +1, half of it to be -1. And then we evolve it using what we call a slice and dice strategy. That is, you apply piecewise constant shear flows alternating vertical with horizontal, and you let them act on progressively smaller times. So at each step, complete step, in half the time. So if you don't know what the shear flow is, that's for the students. The velocity fields is written like this. The horizontal shear, the vertical component is 0, and the horizontal component just depends on the other variable, the vertical variable. So these are automatically divergence free. And the profile of the shear is this function u1. In this case, it's a piecewise constant. So in the picture, for example, I keep the top fixed and I move the bottom. Actually, in this evolution, checkerboard evolution, I do the opposite. I keep the bottom fixed and I move the top half. And so let's look at what we do. So the first step, we move the top half and exactly one length of the torus. Okay, and so we got this checkerboard pattern, so time equal 1/2, and then I apply the same exact flow but in the vertical direction. And so you see at time t 1/2 + 1/2, I have recreated exact replicas of the initial configuration. So this gives rise to what we call a self-similar mixing, because now that I replicated exactly the initial configuration, I just repeat the same construction. The point is that this negative sublet norm has a very nice behavior under rescaling. And you can prove that from step 0 to step 1, so from time 0 to time 1, the 2 steps in the construction, the scale has gone down by 1/2. And so the h-1 norm has also gone down by 1/2. Now, keep in mind, we are not rescaling the torus. Okay, so this is not the same rescaling that you would have in the whole space. So the size of the box is the same. And so, first of all, you see immediately that if you run this algorithm infinitely many times, of course, you will drive the h-1 norm to 0. Okay, you drive it with a factor of 2 to the -n. Right? But at what times? Well, the perfect mixing will happen exactly at the time which is the sum of this geometric series, and so it's time 2. Okay, so you have driven the h-1 norm to 0 exactly at time 2. This is perfect, perfect mixing in finite time, but of course one configuration. Okay, and I will claim later on that in fact, in some sense, this is optimal in this under this constraint. Okay, so this is an example of what I call self-similar mixing. So let me explain more generally what we mean by this. Okay, so we're gonna say that mixing is self-similar if at the certain times the configurations of the tracer at that time is obtained by the previous time step by making a scaling. Okay, so it's an exact. So you're making a certain number of exact copies of the previous configurations on the tools. So here is pictures when you take the cat as the initial configuration, you replace it. And then it's very easy to see what happens to the h-1 norm because you simply rescale. Okay, and so what you observe is that if you are in case A, that is, you control the sublet norm for s less than 1, for example, the energy norm, then in fact you get finite time perfect mixing with a bound that's also that you can compute. So you get in fact a linear bound in the case of energy. Now, if you go to B, but S is 1, okay, so you control the gradient of the velocity in P, then you get an exponential in time mixing, and you already know that you cannot have finite time mixing because you have uniqueness of the normalized solution. But you do get exponential in time mixing. And for case C, where you control the higher norms, okay, so the moment that S is greater than 1, then the self-similar mixing will give you polynomial in time decay, okay? So finite time exponential polynomial. And what I will show, well, we already showed that this is optimal in case A, okay? I will show next that this is optimal in case B, okay? But this is not optimal in case C. This is suboptimal because the optimal rate, in fact, is exponential. And even if you didn't know what the optimal rate is, of course, this norm is stronger than this. So if the lower bound is exponential for S equal 1, it has to be at least exponential for the other case. Okay, so let me show you that you have that this exponential lower bound is in fact achieved. Okay, in the case where you control one derivative in L. So that's what I would call exponential mixing. So I would say that you mix state exponentially if there are constants, which of course depends on you and possibly also on the initial condition, such that the mixing scale, and I will take the functional mixing scale, as I said this morning, decays exponentially in time. And so if you think of Bresson conjecture, you do expect an exponential lower bound if U is at 1 in time with values in W1P, at least for p greater than 1. The example that I will present, you have U uniformly in time with values in W1. And in fact, under that constraint, you can actually prove that you have a lower bound on the mixing scale, which is exponential. This was proved by Gautam, Sasha Kiseler, and Shu in 2013. There is also different approaches. I will mention those by Christian, for example. We'll mention those in the next slides. But I want to spend a little bit of time on this lemma because it relates directly to Bresson conjecture. And it was also mentioned, uses something that was also mentioned by Zora. So let me state the theorem. So you start out by taking a bounded function in L infinity, again, average 0. This is my standing assumption. And I'm going to take U to be a regular time-dependent flow, okay? And then for any P, so U will be smooth, so that I can do an estimate for any P. So for any P between 1 and infinity, but not 1, so you can estimate the from below the rate of decay of the functional scales with constant, which depends on the super level set of data points. So you have to define a super level set here, okay, and they depend on a lambda, so I have to fix a lambda between 0 and 1. And so this says that the functional scale is bounded below by the exponential of the integral in time of the gradient to be in P, but with constants which depend on theta 0 and lambda, of course, and P. The point is that these constants are not just in terms of a norm of theta 0. They are also in terms of, in some sense, the geometry of the initial tracer, which in this case are encoded in the size of these super level sets. Okay? But nevertheless, you have an exponential lower bound, which is what we expect. So you can rigorously prove that you cannot do better than that exponential. And so let me make a couple of remarks. First of all, there is an independent proof of a similar bound by Christian, but using a different technique, so using optimal transport. And so it uses the Monge-Cantor Ridge distance, tau, to measure how far the tracer, the configuration of the tracer field are. And then you also use the fact that the Monge-Cantor distance is controlled by the functional mixing scheme. But I will just give a very rough sketch of the proof of Gautam's and Sasha's result, because that directly ties into the Bresson conjectures. So first of all, you have to relax a little bit the notion of axial mixed set to go to semi-mixed, okay? So semi-mixed simply means that you have a one-sided bounds in the definition of mix that we have. And then you do basically a proof by contradiction. So you prove that there exists a constant, okay, which of course depends on lambda and also on this kappa, although this kappa in some sense less important, such that if the H-1 norm is small enough, okay, then the corresponding level set is semi-mixed. And then you relate being semi-mixed to bounds on the flow. So the idea of the proof is that if I control the H-1 norm, you control the size of the level sets in terms of being semi-mixed. And then if I'm semi-mixed, then I can control bounds from below on the effective velocity. So what they prove is that if the image of the level sets under the flow is epsilon semi-mixed, then the integral in time of the LP norm of the gradient of velocity cannot be too small. So you have a logarithmic lower bound, and then you argue by contradiction to get that. Okay. So I wanted to say words. I guess this is really not a proof; it's just really a skeleton of the proof. But I wanted to put it here to show that this proof is not an energy estimate. Okay, so while for finite perfect mixing, I could simply do a simple energy estimate. Charlie and I tried for years to prove this using energy estimate. We failed, okay, because it's really not a proof by energy estimate. It's really proof to use geometric measure argument. And so that tells you that, you know, it's a more significantly more delicate argument than to expect. Nevertheless, we have. Now the question is it achieved? Okay, can you actually construct flows and initial condition that achieve that exponential lower bound? And the answer is yes. And let me say here that, you know, so there are many classical examples in dynamical system of exponentially mixing maps. So we work in 2D, which is more constrained. Okay, so keep that in mind. For example, the cat map, the baker's map. So here, baker's is literally in the sense of baking because it's folding and stretching, folding and stretching, folding, which is what you do if you make bread. Okay. And there are some examples of flows in higher dimensions, but on non-flat magnet. Of course, if you allow the velocity to be very rough, then the situation is different. But here I'm talking about it in classical theory. Okay. Here, on the other hand, we insist, first of all, on flows and not on map. And secondly, we want to prescribe the regularity of the velocity. Okay. So that makes the problem, in some sense, the result from dynamical system in the deterministic context less applicable. It will be different in the random context. So what I will present here is a geometric construction due to this joint work with Gianluca Crippa and Giovanni Alberti that was first announced in 2014, but then the actual paper came out in 2019 that yield exponentially mixing flows with velocity u, which is W1p for any p, including infinity. So we have a Lipschitz continuous example as well. But we only prove that you mix exponentially certain very special initial data. First of all, these are binary function again, and they are we basically mix two configurations. Okay. So the reason why I want to present this construction, which has really been superseded by very recent development, is because it has application to other problems and it's simple enough that you can actually, you know, again, for the student and for people who are not expert in this area, that really can be presented easily enough, you know, in a normal amount of time. But it has application to other problems, for example, loss of regularity, and I will discuss about that, and also anomalous dissipation. I said that this has been superseded by a recent example. There were also different but related construction at the same time as ours. I will mention those in the next slide. But recently there has really been a flurry of activities. So the latest one is by Elgindilis and Mappingly, and it's literally like 2 weeks ago on arXiv. I still have to really digest the results, so I hope I don't butcher it, but the point is that they prove that if you take a time periodic, certain time periodic Lipschitz flow, which is obtained by alternating independent piecewise linear shear flows, that is in fact exponential mixing. And this is a universal exponential mixing. So this, I tried with my collaborator to prove this also for years, but we failed. And they have a very clever way to do this, as I understand it, okay? It's a perturbation argument. And the fact that the time one image of alternating piecewise linear flow is a piecewise toral automorphism. So an automorphism of the torus under certain conditions like that. So in some sense, you discretize the problem, okay, then you reduce maps, and then the great difficulty is to control what happens, which is done by a subtle perturbation arc. Now, there has also been a lot of results by Sam in particular, and Jacob, and also Alex Blumenthal, where you introduce randomness. So if you introduce randomness, things are, you know, much better, okay? And you, in some sense, you could accept that because mixing has to do with the correlation. So if you introduce randomness, that the correlation should be better. And also because the theory of random dynamical system, you can say a lot more about random dynamical system. I'm definitely not an expert, so I will let Sam to discuss that. But I just want to say one word, okay, that they can prove that they can construct exponential mixing flow that are regular in space, but in fact rough in time. So for example, solution of the 2D Navier-Stokes equation, these are real flows, okay, not fake flows, like, you know, the ones that I would present in some sense, with a certain stochastic force. And after the work last year, so there's been a lot of development in the last, say, 2 or 3 years, what has been for a long time considered in the community as a mixing flow, it's called the Pierre-Humbert flow. And is again rather simple. You take alternating sine shear flows, so the profile is assigned, but with a random phase shift, that this is exponential mixing. And this was proved last year by Alex, Michele Cotti-Zelati, and Balani. I have trouble pronouncing his last name. And you can also, and this is very recent work of Cooperman as well, you can also take fixed shears, but at a random interval of time. And I should say that all this recent development, all of these are universal mixer. That is, they mix all the initial conditions in a dense subset. Okay? So all of this makes the theory rather settled, at least in some ways. And as I said, at the time that we presented this work, there were also related construction by Andre, and I will comment about them a bit later. So, let me present our results. So our approach is a completely geometric approach to constructing the flow, and that will mix optimal only a binary function, although this last condition can be relaxed somewhat. So in other words, you're still going to be +1, -1 on most part of the domain, but instead of having a sharp transition, you can kind of interpolate a little bit. But for simplicity, I will just present the case of a binary function. So again, the initial condition is +1 on the certain set and -1 on the complement. Then the size of the set will be 1/2 of the 2's. So our idea is very simple. So we will prescribe the evolution of the set A. And then we're going to show that there exists a velocity field U that realizes the given evolution. And the delicate part here is not so much show that the vector field exists, but control the norms, control the regularity of the velocity U as you go through the evolution of this. There will be 2 examples. One will be a Sobolev example, that is, the velocity will be uniformly in time with values in W1P for any P. So the same velocity here works for any P except infinity. And because you're not in the Lipschitz class, you can allow topological changes. So the evolution of the set A contains a pinching singularity. And this mixing will be self-similar. So the construction will be totally self-similar. And then I will say one word. I won't go into the detail, but I will show you some picture of the Lipschitz example that's significantly more involved. So the velocity is uniformly in time, Lipschitz in space. Of course, you cannot have topological changes in this case. It's not self-similar, but it's quasi-self-similar. What I mean by this is that the tracer configuration at later times is obtained from a finite family of configuration. Okay, so it's not an exact replica, but it's close to being an exact replica in some sense. So I will show you some pictures. And the key idea here is that basically we follow the step of the construction of the Peano curve, which is a space-leaving curve. So that's why we get it. So, as I said, there were related constructions. In the work of Yao and Zlatosh, what they have a construction which is analytic, is non-geometric, of exponential mixer. So in the work of Yao and Zlatosh, their function, they are in some sense still close to binary. The building blocks in their construction are close to cellular flows. The regularity is uniformly in time with values from P for P in a certain range around 2. And then later on, and I forgot to put its work of El-Guindi and Zlatosh, was generalized to the case of almost universal mixer. And here's where the Baker's map comes in. So they use the fact that the Baker's map, again, can be realized as a time one image of shear flows. And here they can go to regularity higher than 1. So this is, at that time, was the only example when you go for S greater than 1, with P close to 2. So there is a relationship between S and P here. And in this works, there's also another very interesting thing. That's some example of unmixing. And it makes sense that, first of all, the equations are reversible. But secondly, if you think about doing mixing, think of the self-similar example, which I will present. So you mix optimally, but you mix optimally locally, okay? And then you replace it. And so in general, if you mix optimally locally and you go down in scale, to really mix optimally globally, you will have at some point to unmix and to kind of communicate information between adjacent parts of the domain. And if you have separatrices or stagnation points, these are your enemies, of course. So that's the case where you would have to unmix at some time. Okay. So this was a very interesting example that I had. Okay, but our approach is much simpler. Our approach is simply a geometric approach. So I will spend a little bit of time introducing some notations. We will use paths, curves, which will correspond to the evolution of the boundary of time dependence. So let me explain. So for us, paths will be a map from an interval of time in the torus. Okay. The image will be a curve, and we'll assume that the path is a list of class C1, in fact, ideally of class CF for us to report 2. And we will also have time-dependent paths. So here there will be 2 parameters. One, and I'll try to be consistent, S, which is the arc length or any kind of parameter along the curve. But then we move the curve, right? So there will be time, which will give the movement of the paths. So we will have a time-dependent paths. Now is a map on the cross product of 2 time interval into torus, or you could do the construction also on R2 here. All our construction are local. So you can think that they are in the torus or in R2. It's the same thing. Then the notation would be that every time you see a dot, that's the derivative along the curve. And if I put a subscript t or a partial derivative, that with respect to time. Okay. So we will have an adaptive frame. So there will be a tangential a vector tau and a normal vector eta. Of course, I will write them as function of the parameter along the curve. Of course, they're really function of the point along the curve given by the parameterization. And similarly, if I have a time-dependent path, it will be time-dependent frames. And I will orient all curves positively, and I'll choose the normal in the standard way as the rotated by 90 degrees counterclockwise of the tangential vector. So you can write it in terms of the derivative of the parameterization. And if you have a time-dependent path, a key quantity in our construction will be the normal velocity of the curve, which I will denote by Vn. And you can compute it by simply taking the dot product between the time derivative of gamma and the normal. Okay. So we'll also have time-dependent domains. So this will be select value functions from an interval in time into subsets of R2. And we're always going to assume that our sets are regular. Okay, a list of class C1. And the normal velocity in this case will be the outer velocity given by this formula here on the boundary of the set. So as you can see, this is sort of very classical geometry. Now, what is maybe slightly less classical is this idea of a compatible vector fields. So we're going to say that a vector field U is compatible with a time-dependent domain set E if the normal velocity of E, as I introduced it in the previous slides, is exactly given by the normal component of the vector field. So if U is regular and compatible and phi is the flow of U, then you have this very nice fact that the image of the set at any given point give you exactly, under the flow of U, give you exactly the set at the later time. And that's also true of the boundary. And that's why we can reduce to just study what happens on the boundary of the set. Okay. So in fact, you have to, so if the set is not connected, which will be our case, in fact, you have to do this for each connected component because then they're Jordan curves, so you can always distinguish what's inside and outside. But to sometimes this is less important. The key point is that if you have compatibility, then if you take theta to be the characteristic function of the set ET, then this exactly is the distributional solution of the transfer equation with advective velocity U and initial data given by the characteristic function of the mean. So you see, then we can construct a solution simply by constructing compatible vector fields given the evolution of this. That's the idea. So the construction of the exponential mixer is based on this lemma, which is of independent interest. We call it the smooth evolution lemma. If you give me a time-dependent smooth set, such that the measure of each connected component of ET is conserved, then there exists a smooth divergence free vector field U that is compatible with it. And so in all of my construction, I will simply tell you what the time evolution of E is. I will be guaranteed the existence of the flow. I will have to be careful going through topological changes, but then I will also need to be careful to control the bounds on the norm of the vector field G. Okay? But the idea is very simple. So let me give you a sketch of the proof of this lemma. Okay. So we use a string function. In fact, this is not needed, but because we are in R2, that simplifies some things. So the string function, I will denote it by a little sign, is given U is divergence free. So into this, the rotated gradient of the string function. And the advantage of using the string function is that if you cut off a divergence free vector field in general, it will not be divergence free. But if you cut off the string function, then the associated vector field is still divergence free. So I will be able to localize U by cutting off the string function, maintaining the divergence. And that means that it will be enough to define psi in the tubular neighborhood of the bar. Yes. 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 Yes, I will be able to. So all my constructions will be local, okay, around, and then I can extend the flow as I want outside. That's the advantage of doing this. So I only need to construct U in a certain region, and then you can, extend it by anything you want outside, because it will not affect the mixing. So that's, so I will give you only the construction of the stream function in the tubular neighborhood of the boundary of the set. And we will do it this, okay, we will foliate the neighborhood. Remember that except through a singularity, these are very smooth curve and sets. So first of all, the tubular neighborhood is well defined. And secondly, that needs a foliation by smooth curves, which I will denote by gamma alpha. So now there are three parameters. There is the S is the parameter along the curve, say arc length, T is time, and alpha indicates on which curve of the foliation you are. And on each gamma alpha, I will define a stream function. For simplicity, I will write it directly as a function of S and T, but of course it's psi of X of or gamma of S of T, okay? And I define it as the solution of the following family of ODEs in S. The tangential derivative of psi is exactly equal to the normal derivative of the curve. So for each fixed alpha, this should depend on alpha. I didn't write it because the notation is already heavy. And I'm also fixing T. So alpha and T are fixed, and then in S, I solve this ODE. And so on each curve, I have a well-defined function, but does it really represent function in the neighborhood of the set? And that's the question. And it turns out that this is true if the function psi is periodic in S. And that follows from the following lemma. So let's take gamma to be a CK cross curve and V a CK function that integrates to 0 along the curve. So then there exists on each neighborhood of the curve, defined in terms of the distance to the curve. So given R bar, which tells you how far you go from the curve, there exists a autonomous vector field U that has the following property, that the normal component is exactly this function V, and the support of U is within this neighborhood. So let me do the proof of the lemma for U, okay? So let's call gamma the parameterization of the curve, and let's choose a point which I can choose arbitrarily, but I will fix it X naught on gamma. And then I will need to localize my construction. So I introduce a standard cutoff in one dimension, because I will localize along the curve. So G will be a smooth function from R to R, G of 0 equal to 1, and say with support between -1/2 and 1/2. And then I will also pick an R that's between 0 and this R bar. And then I will call B the gamma and R, all the points that are at distance R from gamma. And so you can, so if you denote by B gamma R this neighborhood, then there exists a CK diffeomorphism, because we are in the class CK of the set, that basically flattens out this neighborhood. So in other words, the map a strip onto this neighborhood. That's very classical. And here's how we'll define my stream function, okay? So if X is the image of this neighborhood, so in other words, this diffeomorphism psi simply give you a way to parameterize B, okay? So given any point which correspond to parameter S and gamma in this using this diffeomorphism, so S again still represent the parameter along the curve, then I define the stream function as follows. I take the integral, okay, along the curve of V, okay, and then I multiply by G. this cutoff, of course, normalized, rescaled by R. And then what you can prove is that the tangential derivative of group psi is exactly V. Okay, V is of classic K minus 1, and the support of psi is in a smaller tubular neighborhood of the ones that you started. And you see, once you do this, then you can simply extend by 0. Okay, extend the psi by 0, you take the rotated gradient, that's your vector. So that tells us that we can work local, okay, and we are guaranteed to have the construction of the string function. So if you comment, so you can definitely extend. So this lemma is for one curve, okay. We have time-dependent curves. The extension is straightforward. You can extend the lemma to time-dependent curves, but the function V has to be compatible in the way that I described before. This compatible, then the vector field that I construct will also be compatible. And let me say that the condition that the integral along the curve of V is 0 is a necessary condition. And that's very simple to see because by the divergence theorem. If you want U to be divergence free, apply the divergence theorem, it pops out that this condition must be. And in particular, if you choose V to be the normal velocity of the curve, then in fact the lemma gives you the existence of a vector field which is compatible with the time evolution of the curve. Okay. So our construction will be to give the evolution of the set, and then all of these lemmas which I presented guarantees us the existence of a compatible divergence-free vector field that realizes, that moves the curves in the prescribed. There will be one more concept that I will use, again, very classical. So far, these things are, I mean, we formalize them in a way that was needed for our construction, but they're very classical concept, that of homothetic curves. So I will take a fixed curve and I dilate it by a factor lambda of t. I will call this gamma bar to be the support curve that stays fixed in time. The point is, what do the normal velocity, the frames, and the vector fields U do in this case? Well, if I call V bar x dot and eta bar, where eta bar is the normal to gamma bar, that's time independent, then I can construct the normal to the dilated curves and the normal velocity of the dilated curve of the homothetic curve simply by a scale. And so this is obviously, straightforward. What is a little less straightforward is that if U bar is compatible with gamma bar, which again, I remind you means that the normal component of U bar is exactly the velocity of gamma bar, then the scale vector fields will also be compatible with the homothetic curves. Okay? So we will use all of this concept in our construction, and so we'll do in detail only what's the time? How long do I have? Okay, so I may not finish, but I will start. So I will discuss in detail only the first example, the pinch and singularity. And the reason why I want to do that is because this example shows some interesting phenomena for regular Lagrangian flows that were not known before our example. The mixing will be totally self-similar. So in some sense, I only have to describe what happens at the first step. And then the subsequent steps are just done by a scale. And so what I will do is I will construct, so I will denote by superscript 0 the initial, all the quantities that relate to these initial steps, okay? While lowercase will mean initial time. So we construct a U superscript 0, which is a vector field in L infinity in time with the values in W1P, or any P except infinity, so this is not a Lipschitz case. And in fact, this vector field turns out that it's even more subnet spaces. I can take, of course, any Sobolev space with S less than 1, including P infinity. And I can even go to S greater than 1, but of course the P is severely restricted because I don't want you to village. So in some sense, 0 is in the Sobolev classes that don't matter. And my initial configuration, my theta, in this case, theta naught here, will be the characteristic function of a certain set, and then I subtract a constant simply to normalize things. So in some sense, you can ignore this just to normalize some things. So it's literally the evolution of a time-dependent set. So I will tell you how to construct this. And so this evolution will be as follows. The measure of my set will be constant because I want you to be divergence free. It will always be pi divided by 16. So we subtract here the pi divided by 16 to make this mean 0. But in that sense, it's not that important. And the initial picture of initial configuration is the characteristic function of the set in 0, which is simply the disk center at 0 of radius 1/4. And at time 1, I want this to have evolved into 4 copies of the initial disk at scale 1/2. So this is perfectly self-similar, and then I repeat just by a scale. Okay. So what will happen here is that U naught and theta naught will be smooth, except possibly at times that are multiples of 1/8. Okay. Theta naught will be continuous and transported in between these times. And overall, theta naught will be a weak solution of the transport equation with a Latin velocity U naught. And then you concatenate the step to construct a weak solution for all times. So first step is the construction. So there will be 4 steps, which correspond to go from 0, 1/4, 1/8, 1/8, 1/4, 1/4, 3/8, and then 1/2. Okay. And once I reach here, in fact, I'm already in a self-similar situation in some sense. So I only have to explain to you to go from time t equals 0, time t equal 1/2, and then I can repeat the construction. So step 1 is the construction between 0 and 1/8. And I want a shape like this, okay? And I will, in particular, time t equal 8, this shape will be will have a mirror symmetry. So I will reflect, so it will be obtained by reflecting across the dotted lines here, okay? And going from here to here, the evolution is smooth. You can check that these are simply connected smooth and have the same area. So the smooth evolution level will tell me exactly how to construct the velocity from here to here. And I can also construct it to have support on a certain square Q, which is what I represent here. Okay. So you should think that the torus is a little bigger, and my square Q is what zoom in this neck here. Okay. Remember that the point is to construct pinch and singularities, but you have to do it in a way that the flow is that volume preserving, and you control the norms. Okay. So the construction of the sets and the velocity from 1/8 to 1/4 is really the crux of the construction here. And I'm going to call gamma bar this piece of the curves, okay? And then the entire curves that you see here, I do by mirror symmetry. And of course, there will be an exact construction in the bottom. So I only have to tell you what happens in this space here, okay? And there will be 2 sets. B will be this here, the zoom to the neck, and then this rectangle R will be as in the picture here. So all the action will happen in B, R, and B on the top part, and then by reflection it will work everywhere else. Okay, and I will construct the evolution of this curve gamma in time by homotety. Okay, so it will be done by homotety. So I will define a homotety with factor lambda t that has the property that, of course, I want to do 1 at 1/8, and it will go to 0 at 1/4, where I will have my pinch in singularity. So you should think that this is time 1/8, and this is time 1/4. Okay. And again, it's just enough to construct this piece of the curve here. Okay, and I will do it, and then, okay, so I will construct the curve here, but then of course I have to close my sets, and I will need to do, and I will do it in such a way that, first of all, the boundary of the entire set is a Jordan curve. Moreover, I want to preserve the size of the set, and I want things to happen only in the net. So I do not want to change what happens outside of the ball. Okay, so that nothing will change here. So the reason for that is because I will construct my velocity field inside the ball, the disk B, and then I will just take do nothing flow, say 0. Okay, velocity 0 outside of. So I want E of t to be equal to E1/8 on the complement of the ball B in the square Q where my set lies. Okay. And again, I want to preserve the mirror symmetry. Okay, so I really need to construct only 1/4 and then extend by mirror symmetry. But the smooth evolution lemma, I know in the homothetic framework, I know that there exists a U0 that does what I showed you in pictures. And then I extend it by reflection and by 0 to leave the entire Q. And as I said, U will be obtained by a homothety, so I know exactly how to write it down. And the question is, once you have this, you are locked in, right? The shape of this vector field is given to you. So can you control the norms of U? You can, because you have the choice of how fast you approach the pinch in singularity. And if you choose the homothety in this form here, you can prove that in fact U0 has the needed sum level. Okay. So the shape of the velocity field is completely determined by all these conditions which I imposed above. The only freedom is how fast you approach the pinch in singularity, but that is enough to control the And okay, then we're basically done, because then at the next steps, we proceed very similar to what we have done in step 2. I just showed you a picture of what we do. In some sense, you backtrack some of the construction, you reverse some of the construction that I've done in step 2 to separate the two components of the pinch and singularities into two separate but still mirror symmetric sets. And at each of these two steps, because each of the components now is smooth, you can use the smooth evolution lemma to construct the velocity. So finally, at time t equal 1/2, you have created two exact copies of the initial disk, but with the radius 1/8 instead of 1/4. And then you simply repeat step 1 through 4 to create at time 1 4 copies of the initial disk with radius 1/16. And that's complete the initial step of the construction. And how do you continue? You continue by self-similarity, right? So for each integer n, now you scale the initial velocity, not initial in time, the initial step velocity u0 and the initial step tracer theta 0. And then you concatenate that to give you a mixed solution. Okay, and that's the construction. So and you can check again by rescaling. Remember, we do not rescale the domain. So at each complete step, the h-1 norm has gone down exactly by a factor 1/2. So in infinitely many steps, you have driven the h-1 norm. So I will stop here. I will just say a couple of remarks. So I wanted to go through this construction. First of all, to tell you this is very classical construction. Okay, so we do everything by hand. Okay, and of course that has its own problems in some sense, because if you perturb this construction, things will break down. So it's really not a very stable construction, but it has some nice things. First of all, it shows some pathologies that regular Lagrangian flows that can be arbitrarily close to Lipschitz. You can go as close as you want to Lipschitz, that these regular Lagrangian flows can have. And before our work, this was not known that it could happen. So first of all, the flow can compress a segment to a point, and of course, expand the point to a segment in finite time. And you also have point-wise non-uniqueness of trajectories starting from these segments. This construction has the nice things that it can easily be localized. So as I said, everything happens near the boundary of the set T, this cube. So first of all, you can immediately transport it to R2 with U and theta also still compactly supported. You can also think that it lives in a bounded domain, and you can put any boundary condition you want as long on U and theta as long as they are compact. So this is really a local. And okay, I think that I will stop here. So what I will show you tomorrow is the other construction, which we call the piano snake, because we start out with a strip and we deform it into something that looks like a snake. This is not self-similar, it's quasi-self-similar. And the construction is a lot more involved. So I will, but it follows very similar idea. So I will just show you some picture for that. And then after that, I will show you how to use this example to prove loss of regularity for solution of transport. So let me stop here.